For millennia, humanity has pondered the mysteries of inheritance. How do traits, from eye color to disease susceptibility, pass from one generation to the next? The answer, it turns out, lies within a microscopic masterpiece, deoxyribonucleic acid, or DNA. The story begins in the 19th century, with the work of Gregor Mendel, an Austrian monk. Through meticulous experiments with pea plants, Mendel observed patterns of inheritance, laying the groundwork for the field of genetics. He proposed the existence of discrete factors, now known as genes, that determine the traits of an organism. As scientists began to delve deeper, they discovered chromosomes, thread-like structures within the nucleus of cells. These chromosomes, they realized, were somehow involved in the transmission of genetic information. But the exact nature of this information remained elusive. In the early 20th century, Swiss biochemist Friedrich Miescher isolated a novel substance from the nuclei of white blood cells, which he named nuclein, later renamed nucleic acid. This discovery opened the door to the study of the molecules that would revolutionize our understanding of life. Decades later, through elegant experiments with bacteria and viruses, scientists like Oswald Avery and Alfred Hershey and Martha Chase provided compelling evidence that DNA, not protein, was the carrier of genetic information. The race to decipher the structure of DNA intensified in the mid-20th century. Rosalind Franklin, a brilliant X-ray crystallographer, generated crucial data that revealed the helical structure of DNA. Her work, though largely unrecognized at the time, proved invaluable to James Watson and Francis Crick, two young scientists who, in 1953, published their groundbreaking model of the DNA double helix in the journal Nature. The Watson-Crick model, a double helix resembling a twisted ladder, elegantly explained how genetic information could be stored and replicated. The rungs of this ladder consist of pairs of four chemical bases, adenine, A, thymine, T, guanine, G, and cytosine, C. The specific sequence of these base pairs forms the unique genetic code of every organism. The discovery of the double helix ignited a revolution in molecular biology. Scientists developed techniques to sequence DNA, determining the precise order of base pairs in a gene or even an entire genome. The Human Genome Project, a monumental international effort, successfully mapped the entire human genome, a landmark achievement that opened new avenues of research in medicine and personalized healthcare. Artificial intelligence. The very term sparks visions of sentient machines, futuristic utopias, and dystopian anxieties. But the journey to creating a truly intelligent machine is a long and complex one, a tapestry woven with threads of philosophy, mathematics, and relentless human ingenuity. This is the story of artificial intelligence. The dream of creating artificial beings dates back to antiquity. Myths and legends are filled with tales of mechanical servants and animated statues. But the seeds of modern AI were sown in the fertile ground of mathematics and logic. In the 17th century, Gottfried Wilhelm Leibniz envisioned a universal symbolic language that could represent all knowledge. And in the 19th century, Charles Babbage designed the analytical engine, a mechanical general-purpose computer, laying the groundwork for the machines that would one day host AI. The 20th century witnessed a surge in technological advancements that propelled the field of AI forward. Alan Turing, a brilliant mathematician and codebreaker, is often considered the father of AI. His work on the Enigma machine during World War II demonstrated the power of computation. And in his seminal 1950 paper, Computing Machinery in Intelligence, he proposed the Turing test, a benchmark for machine intelligence that continues to spark debate today. In 1956, a pivotal event took place at Dartmouth College. A group of researchers, including John McCarthy, Marvin Minsky, and Claude Shannon, convened for a workshop that officially launched the field of artificial intelligence. They envisioned a future where machines could think, learn, and solve problems like humans. The early years of AI were marked by optimism and rapid progress. Programs like ELIZA, a simulated therapist, and SHRDLU, a robot that could manipulate blocks in a virtual world, showcased the potential of symbolic AI, which relied on logic and rules to mimic human reasoning. However, the initial enthusiasm was soon tempered by the limitations of early AI techniques. The complexity of real-world problems proved far greater than anticipated, and funding for AI research dwindled, leading to periods known as the AI winter. In the 1980s, AI experienced a resurgence with the development of expert systems, programs designed to mimic the decision-making abilities of human experts in specific domains. These systems found applications in fields like medicine and finance, demonstrating the practical value of AI. The late 20th and early 21st centuries witnessed a paradigm shift in AI, driven by the rise of neural networks and deep learning. Inspired by the structure of the human brain, neural networks are composed of interconnected nodes that learn from data through a process of trial and error. Deep learning, a subset of machine learning, utilizes deep neural networks with multiple layers to extract complex patterns from vast amounts of data. The impact of deep learning has been profound. AI systems can now perform tasks that were once considered the exclusive domain of humans, such as image recognition, natural language processing, and playing complex games like Go. Self-driving cars navigate city streets, virtual assistants answer our questions, and AI-powered medical diagnostics assist doctors in detecting diseases. However, the rapid advancements in AI have also raised concerns about its ethical and societal implications. Issues such as job displacement, algorithmic bias, and the potential for autonomous weapons require careful consideration and responsible development. The debate surrounding AI safety and the future of artificial general intelligence, AGI, continues to intensify. Today, AI research is pushing the boundaries of what is possible. Scientists are exploring new architectures for neural networks, developing AI systems that can learn and adapt in real time, and investigating the potential of quantum computing to accelerate AI development. The roots of the stock market reach back to the dawn of organized trade. Early merchants, traversing the Silk Road and Mediterranean, engaged in rudimentary forms of risk-sharing. Caravans were financed by multiple investors, splitting potential profits and losses. This concept, the foundation of modern equity, took centuries to formalize. The 17th century saw the birth of the first modern stock exchange in Amsterdam. The Dutch East India Company, a behemoth of global trade, required immense capital to fund its voyages. To raise this capital, they issued shares of ownership, allowing individuals to participate in their lucrative ventures. This marked a watershed moment, the creation of tradable securities. The Amsterdam Stock Exchange quickly became a hub of speculation. However, the allure of quick riches led to the infamous tulip mania. Tulip bulbs, once a luxury, became wildly inflated in price, fueled by irrational exuberance. When the bubble burst, fortunes were wiped out, a stark reminder of the inherent volatility of the market. This early crash taught a crucial lesson: speculation without sound fundamentals is a dangerous gamble. Across the English Channel, London followed suit. The South Sea Company, promising vast profits from trade with South America, captivated investors. The company's stock soared, fueled by rumors and manipulated information. But like the tulip mania, the South Sea bubble eventually burst, causing widespread financial ruin. This event led to the enactment of the Bubble Act, aimed at curbing fraudulent schemes and protecting investors. In the nascent United States, the stock market mirrored the nation's growth. The Buttonwood Agreement, signed by 24 brokers under a buttonwood tree on Wall Street, laid the foundation for the New York Stock Exchange. The Industrial Revolution fueled a surge in investment, as companies sought capital to build railroads, factories, and infrastructure. The 1920s witnessed a period of unprecedented prosperity and speculation. The stock market became a symbol of American optimism. However, the unchecked euphoria led to a disastrous crash in 1929. Black Tuesday, October 29, marked the beginning of the Great Depression, a period of economic hardship that shook the world. The crash of 1929 exposed the vulnerabilities of the unregulated market. In response, the U.S. government established the Securities and Exchange Commission, SEC, to oversee the stock market and protect investors. Regulations were implemented to ensure transparency and prevent manipulation. Following World War II, the stock market experienced a period of sustained growth. The rise of institutional investors, such as pension funds and mutual funds, transformed the landscape. The introduction of computers revolutionized trading, allowing for faster and more efficient transactions. The advent of the Internet in the late 20th century ushered in a new era of online trading. The NASDAQ, a computerized exchange, became a hub for technology companies. The dot-com bubble, fueled by irrational exuberance for Internet stocks, mirrored the earlier manias, culminating in a dramatic crash in 2000. The 21st century has been marked by both innovation and volatility. The 2008 financial crisis, triggered by the collapse of the subprime mortgage market, sent shockwaves through the global economy. The crisis exposed the interconnectedness of financial markets and the need for robust regulatory frameworks. Today, the stock market is a complex and dynamic ecosystem. Algorithmic trading, high-frequency trading, and fintech innovations have transformed the way stocks are bought and sold. The market is increasingly globalized, with investors participating from all corners of the world. The stock market, despite its inherent risks, remains a powerful engine of economic growth. It provides a platform for companies to raise capital, for individuals to invest in their future, and for the allocation of resources. As technology continues to evolve and global markets become increasingly interconnected, the stock market will undoubtedly continue to shape the course of human history. In the heart of the digital age, a revolution is brewing within the realms of healthcare and finance. Meet CLEO Genomic AI. It's not just a diagnostic tool, it's a predictive engine, a financial analyst, and a potential game-changer for the future of personalized medicine and biotech investment. At its core, CLEO empowers healthcare professionals with unparalleled diagnostic precision. By analyzing vast genomic datasets, CLEO identifies specific genetic markers associated with diseases, transcending the limitations of traditional symptom-based approaches. This allows for early detection, personalized treatment strategies, and a deeper understanding of disease pathogenesis. Imagine a physician, armed with CLEO's insights, able to pinpoint the precise genetic factors contributing to a patient's illness. CLEO doesn't just diagnose, it prescribes. It generates tailored treatment plans, suggesting optimal drug dosages and therapies based on individual genetic profiles. This level of personalization promises to revolutionize patient care, reducing adverse reactions and maximizing treatment efficacy. CLEO's impact extends beyond the clinic. Its innovative business model generates revenue by offering these diagnostic and prescriptive services to doctors, creating a vital tool for those at the forefront of patient care. Furthermore, CLEO's integrated marketing strategy creates advertising revenue. When CLEO creates a prescription, it can direct healthcare professionals to partnered pharmacies where those medications can be purchased. This creates a revenue stream that is integrated into the diagnostic process. But CLEO's capabilities don't stop there. It leverages the wealth of data it collects to manage a sophisticated biotech investment portfolio. By analyzing the financial performance of publicly listed pharmaceutical companies, including revenue, profitability, and R&D expenditures, CLEO assesses their financial stability and growth potential. CLEO integrates its genomic insights with comprehensive financial data and market share analysis. This financial analysis is further enriched by market share data, which reveals the competitive landscape and identifies companies with established market dominance in relevant therapeutic areas. CLEO doesn't just look at numbers, it understands the underlying science. For instance, if CLEO identifies a surge in a specific infectious disease, it will analyze the market share of companies producing existing treatments for that disease. It will also analyze the R&D pipelines of companies attempting to make new treatments. This analysis will determine which companies are best poised to capitalize on the increased demand. At the heart of CLEO's methodology lies its ability to diagnose diseases with unparalleled accuracy. This diagnostic capability is not merely a clinical tool, it serves as a critical foundation for investment decisions. By analyzing genomic data, CLEO can identify the specific genetic markers associated with a disease, enabling a deeper understanding of its pathogenesis and potential treatment pathways. This precision diagnosis transcends traditional symptom-based approaches, allowing for early detection and personalized treatment strategies. Furthermore, CLEO's ability to analyze vast genomic datasets enables the identification of emerging disease variants and potential drug targets, providing a crucial edge in predicting future outbreaks. Imagine CLEO predicting the next pandemic before it even begins, allowing for rapid development of vaccines and treatments. CLEO has transformed the way we approach patient care. The level of precision it provides is simply unparalleled. CLEO's ability to integrate genomic insights with financial analysis is a game-changer for biotech investment. It gives us a level of predictive power we've never had before. CLEO represents a paradigm shift in the intersection of healthcare and finance. It's a testament to the power of AI to unlock the secrets of the human genome and to drive innovation in both medicine and investment. As CLEO continues to evolve, its potential to transform lives and shape industries is undeniable. It's a glimpse into a future where personalized medicine is the norm, where disease outbreaks are predicted and prevented, and where investment decisions are guided by the wisdom of the genome. The algorithmic oracle has arrived, and its impact is only just beginning. To participate in the future of healthcare and AI investment, users can visit our website and purchase CLEO tokens, available on the Binance blockchain. Each CLEO coin is backed by the performance of CLEO's strategically managed biotech fund, which includes holdings in leading pharmaceutical companies such as Novartis, Eli Lilly, Sanofi, AstraZeneca, and other prominent industry players. This backing provides a tangible link between the digital asset and the real-world value of established and innovative biotech enterprises.